quantified by the elastic models such as Young modulus, bulk modulus, or shear modulus, which measure the amount of stress needed to achieve a unit of strain. A higher modulus indicates that the material is harder to deform. The SI unit of this modulus is the Pascal PA. The material elastic limit or yield strength is the maximum stress that can arise before the onset of plastic deformation. The SI unit is also the Pascal PA. Overview: when an elastic material is deformed due to an external force, it experiences internal resistance to the deformation and restores it to its original state. And if the external force is no longer applied, there are various elastic moduli such as Young's modulus, the shear modulus, and the bulk modulus, all of which are measures of the inherent elastic properties of a material as a resistance to deformation under an applied load. The various moduli apply to different kinds of deformation. For instance, Young's modulus applies to extension compression of a body appears. The shear modulus applies to shear. Young's modulus and the shear modulus are only for solids, whereas the bulk modulus is for solids, liquid, and gases. In the elasticity of the material is described by a stress-strain curve, which shows the relation between stress, the average restorative internal force per unit area, and strain, the relative deformation. The curve is generally non-linear, but it can, by use of a Taylor series, be approximated as linear for sufficiently small deformations, in which higher order terms are negligible. If the material is isotropic, the line-derived stress-strain relationship is called Hooke's law, which is often presumed to apply up to the elastic limit for most metals or crystalline materials, whereas non-linear elasticity is generally required to model large deformations of rubbery materials. Even in the elastic range for even higher stresses, materials exhibit plastic behavior, that is, they deform irreversibly and do not return to their original shape after stress is no longer applied. For rubber-like materials such as elastomers, the slope of the stress-strain curve increases with stress, meaning that rubbers progressively become more difficult to stretch, while for most metals the gradient decreases at very high stresses, meaning that they progressively become easier to stretch. Elasticity is not exhibited only by solids. Non-Newtonian fluids such as viscoelastic fluids will also exhibit elasticity in certain conditions quantified by the Deborah number. In response to a small rapidly applied and removed strain, these fluids may deform and then return to their original shape. Under larger strains or strains applied for longer periods for time, these fluids may start to flow like a viscous liquid. Because the elasticity of a material is described in terms of a stress-strain relation, it is essential that the terms stress and strain are defined without ambiguity. Typically, two types of relation are considered. The first type deals with materials that are elastic only for small strains. The second deals with materials that are not limited to small strains. Clearly, the second type of relation is more general in the sense that it must include the first type as a special case. For small strains, the measure of a strain that is used in the Cauchy stress, while the measure of strain that is used in the infinitesimal strain tensor. The resulting predicted material behavior term linear elasticity, which for isotropic media is called the generalized Hooke's law. And Cauchy elastic materials and hypoelastic materials are models that extend Hooke's law to allow for the possibility of large rotations, large distortions, and intrinsic or induced anisotropy. For more general situations, any of the number of stress measures can be used, and it's generally described but not required. But the elastic stress strain relation be phrased in terms of finite strain measure, that is work conjugate to the selected stress measure, i.e. the time integral of the inner product of the stress measures with the rate of the strain measure should be equal to the change in internal energy for any adiabatic processes that remains below the elastic limit. Units, that's a unit of electricity, and the elastic modulus is the Pascal PA. The unit is defined as force per unit area, generally a measurement of pressure, which is mechanic corresponds to stress. The Pascal and therefore electricity have the dimension L-1, m dot T -2. For most commonly used engineering materials, the elastic modulus is on the scale gigapascals, GPa 10-9 PA. Linear elasticity and noted above for small deformations. Most elastic materials such as springs exhibit linear elasticity and can be derived by a linear relation between the stress and strain. This relationship is known as Hooke's law. A geometry dependent version of idea was first formulated by Robert Hooke in 1675 as a Latin anagram coinociative. He published the answer in 1678. Duty tensio sig vis, meaning as the extension, so the force a linear relationship commonly referred to as Hooke's law. This law can be stated as a relation between tensile force F and corresponding extension displacement X. F is equal to Kx, where K is the constant known as the rate or spring constant. It can also be stated as a relationship between stress and strain, EE, where E is known as Young modulus. Also, the general proportionality constant between stress and strain in 3 dimensions is the fourth order tensor called stiffness. System that exhibit symmetry such as a one-dimensional rod can often be reduced to application of Hooke's law. Finite elasticity, the elastic behavior of objects that undergo finite deformation has been described using a number of models such as Cauchy elastic material models, hypoelastic material models, and hyperelastic material models. The deformation gradient F is the primary deformation measure used in finite strain theory. Cauchy elastic materials and Cauchy elastic materials. A material is said to be Cauchy elastic if the Cauchy stress tensor is a function of the deformation gradient F alone. It is generally incorrect to state that Cauchy stress is a function of merely a strain tensor. As such, a model lacks crucial information about material rotation needed to produce correct result for an anisotropic medium subjected to vertical extension in comparison to the same extension applied horizontally and then subjected to a 90-degree rotation. Both these deformations have the same spatial strain tensors, yet must produce different values of the Cauchy stress tensor. Even tough, the stress in a Cauchy elastic material depends only the state of deformation. The work done by stresses might depend on the path of deformation. Therefore, Cauchy elasticity includes non-conservative, non-hyperelastic models in which work of deformation is path dependent, as well as conservative hyperelastic material models for which stress can be derived from a scalar elastic potential function. And hypoelastic material can be rigorously defined as one that is modeled using a constitutive equation satisfying the following two criteria. The Cauchy stress at time t depends only on the order in which the body has occupied its past configuration, but not on the time rate at which these past configurations were traversed. As a special case, this criterion includes a Cauchy elastic material for which the current stress depends only on the current configuration rather than the history of past configurations. This is a tensor valued function G such that O is equal to O, comma L, in which the material is the material rate of the Cauchy stress tensor and L is the spatial velocity gradient tensor. If only these two original criteria are used to define hypoelasticity, then hyperelasticity would be included as a special case, which prompts some constitutive modelers to append a third criterion that specifically requires a hypoelastic model to not be hyperelastic, i.e. hyperelasticity implies that stress is not derivable from an energy potential. If this third criterion is adopted, it follows that a hypoelastic material might admit non-conservative adiabatic loading paths that start and end with the same deformation gradient but do not start and end at the same internal energy. Note that the second criterion requires only that the function g exists as detailed in the main hypoelastic material article. Specific formulations of hypoelastic models typically employ so-called objective rates, so that the g function exists only implicitly and is typically needed explicitly only for numerical stress updates performed via direct integration of the actual not objective stress rate. And in hyperelastic material applications, linear elasticity is used widely in the design and analysis structures such as beams, plates, and shells and sandwich composites. The theory is also the basis of much of fracture mechanics. Hyperelasticity is primarily used to determine the response of elastomer-based objects such as gaskets and of biological materials such as soft tissues and cell membranes. Factors affecting elasticity in a given isotropic solid with non-theoretical elasticity for the bulk material in terms of Young's modulus. The effective elasticity will be governed by porosity. Generally, a more porous material will exhibit lower stiffness. More specifically, the fraction of pores, their distribution at different sizes, and the nature of the fluid with which they are filled give rise to different elastic behaviors in solids. For isotropic materials containing cracks, the presence of fractures affects the Young's and the shear moduli perpendicular to the planes of the cracks, which decreases Young modulus faster than the shear modulus as the fracture depth increases, indicating that the presence of cracks makes bodies brittle. Microscopically, the stress-strain relationship of material is in general governed by the Helmholtz free energy thermodynamic quantity. Molecules settle in the configuration which minimizes the free energy subject to constraint derived from their structure, and depending on whether the energy or entropy term dominates the free energy, material can broadly be classified as energy elastic and entropy elastic. As such, microscopic factors affecting the free energy, such as the equilibrium distance between molecules, can affect the elasticity of material. For instance, in inorganic material as the equilibrium difference between molecules at 0 K increases, the bulk modulus decreases. The effect of temperature on elasticity is difficult to isolate different because there are numerous factors affecting it. For instance, the bulk modulus of a material dependent on the form of its lattice, its behavior under expansion, as well as the vibrations of the molecules, all of which are dependent on temperature. And these more topics are elasticity tensor, lithography, tactile imaging, elastic modulus, linear elasticity, pseudo elasticity, resilience, rubber elasticity, stiffness, ductility. So friends, how is my topic today about which I guide you elasticity in physics. I hope you like. So now I am go to my new topics. Take care, love is. We will meet our next new best topics. So I am go. Take care. Love you, love is. Ding 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 ding.